This is what we're here for tonight, yes, to drift, to wonder, to let the mind settle into those deep questions that have puzzled humanity for as long as we've looked up at the stars, really. Let me tell you something curious, something that kept me awake many nights when I was younger, working in that patent office in Bern. I would sit there, you see, examining applications, and my mind would wander. It would wander to the nature of time itself. Time. This thing we take so granted, this thing that flows, or does it flow? You see, this is where it all begins, with a simple question that isn't simple at all. Imagine, if you will, that you are riding on a beam of light. Riding on it, yes, like you might ride a bicycle through the Swiss countryside. What would you see? This thought, this thought came to me when I was just 16 years old, and it wouldn't leave me alone. It haunted me, you see, in the most wonderful way. Because if you could ride on that beam of light, traveling at this incredible speed of 299, 792, 458 meters per second, what would the world look like? Would time stop? Would light itself appear frozen? The thing is, you see, the thing is, light is peculiar. It doesn't behave like anything else in our experience. If you're in a train moving through a station and you throw a ball forward, the speed of that ball is your throwing speed plus the speed of the train, yes? This makes sense to us. It feels natural. But light doesn't do this. Light always travels at the same speed, no matter who is observing it, no matter how fast you yourself are moving. This bothered people for a long time. There was this idea, you see, this beautiful idea, really, of something called the luminiferous ether. They thought space must be filled with this invisible substance, this ether, through which light waves would propagate, just like sound waves need air to travel through. It made sense, didn't it? Everything we knew about waves required a medium. But then came these two clever men, Michelson and Morley, in 1887. They conducted an experiment, a very precise experiment with mirrors and light beams, trying to detect this ether. If Earth was moving through this cosmic ether, they reasoned, then light should travel at different speeds depending on whether it was moving with or against Earth's motion through this medium. It's like it's like swimming in a river, yes? Swimming upstream is harder than swimming downstream. But they found nothing, nothing at all. The speed of light was the same in all directions at all times. This was deeply puzzling to the scientific community. Some tried to explain it away, to modify the theory, to add complexity. But sometimes, you see, sometimes the answer is not in adding complexity, but in removing assumptions we didn't even know we were making. And what was that assumption? It was about time itself. We assumed, without really thinking about it, that time is absolute, that it flows the same for everyone, everywhere. That if I look at my watch here and you look at your watch there, even if we're moving very differently, we would agree on what time it is, on how much time has passed. But but what if this isn't true? What if time itself is flexible, malleable, dependent on how fast you're moving? This seems absurd at first, doesn't it? Our everyday experience tells us time is time. A second is a second is a second. Yet, Yet, when we really think about it, when we follow the logic of that constant speed of light, we arrive at something extraordinary. Let me paint you a picture, a thought experiment. You're standing on a train platform, yes? And a train passes by you very, very fast. On that train, there's someone with a flashlight, and they shine it up toward the ceiling of the train car. From their perspective, sitting on the train, the light goes straight up and straight back down. Simple. The distance is, let's say, 3 meters. But you, standing on the platform, you see something different. From your perspective, while that light is traveling up to the ceiling, the train has moved forward. So the path of the light isn't straight up and down, it's diagonal. It travels a longer distance, forming a triangle. Now, here's the crucial part, the part that changes everything. That light beam must travel at the same speed for both of you. This is what experiments tell us over and over. The speed of light is constant. But if the light travels a longer path for you than for the person on the train, and it travels at the same speed, then you see, then the only way this works is if time itself passes differently. Time must run slower for the person on the train from your perspective, just slightly, just enough to make the mathematics work out. This is time dilation, you see, the stretching of time itself. When I first realized this, when I first worked through the mathematics in 1905, it was it was like seeing behind a curtain. The universe had been hiding this truth in plain sight. Time and space are not separate things, not independent things. They are woven together into what we now call space-time. Four dimensions, three of space and one of time, all interconnected, all influencing each other. Now, you might be thinking, but I've never noticed time running differently. I've been on trains, on airplanes, and my watch keeps the same time as everyone else's. And you're right to think this, because at the speeds we normally experience, these effects are tiny, vanishingly small. You would need to travel at a significant fraction of light speed to notice anything unusual. But here's what's remarkable. What fills me with wonder even now, we have measured this. We have taken atomic clocks, clocks so precise they can measure billionths of a second, and we've flown them on airplanes around the world. And when they landed, they were behind the clocks that stayed on the ground, just by nanoseconds, just by tiny amounts, but measurably, undeniably different. Time had genuinely passed more slowly for those traveling clocks. The astronauts on the International Space Station, orbiting Earth at about 28,000 kilometers per hour, they are aging slower than we are down here. Only by milliseconds over months, yes, but it's real. It's happening. They are, in a very real sense, traveling into our future, even if only by the tiniest amount. And then there's something even stranger, something that follows from the same reasoning. If time can stretch, what about space? What about distance itself? It turns out, it turns out that distances contract in the direction of motion. If you're in a spaceship traveling very fast, the universe ahead of you would be compressed, squashed. A journey that should take years could take less time, not because you're going faster than light, nothing can do that, but because the space between your starting point and your destination has literally become shorter for you. This leads us to something that bothered people, still bothers people sometimes, the twin paradox, they call it. Imagine two twins, yes? One stays on Earth, the other travels on a spaceship to a distant star at very high speed and returns. When the traveling twin comes back, they will be younger than their sibling who stayed home, genuinely younger. They will have experienced less time passing. Their heart will have beaten fewer times. They will have had fewer thoughts, fewer breaths. This seems paradoxical because you might think, isn't motion relative? Couldn't the traveling twins say that Earth moved away from them and came back? Why isn't it symmetrical? The answer lies in acceleration, in the fact that the traveling twin had to turn around, had to change direction. That breaking of symmetry, that acceleration, makes all the difference. This has been tested too, not with twins, but with particles called muons. These particles are created high in Earth's atmosphere when cosmic rays strike air molecules. They're unstable, you see. They decay very quickly in about 2 microseconds. At their speed, even traveling nearly at light speed, they shouldn't be able to reach the ground before they decay. The distance is too great, the time too short, but they do reach the ground. We detect them all the time. Why? Because from our perspective, their clocks are running slow due to time dilation. They live longer from our point of view. And from their perspective, if muons could think, the thickness of our atmosphere would be contracted shorter, so they have less distance to travel. Both views are correct. Both describe the same reality from different perspectives. You see, this is what I find so beautiful about these theories. They're not just abstract mathematics, not just philosophy. They make predictions. specific predictions about how the universe behaves, and then we can test them. We can look at the universe and ask, is this really how you work? And the universe answers consistently, yes, this is how I work. Now, all of this, everything I've described so far, comes from what we call special relativity. Special because it deals with a special case, objects moving at constant velocities, not accelerating. But the universe is full of acceleration, full of gravity, and gravity. Oh, gravity is where things become even more interesting, even more dreamlike in their strangeness. Gravity is perhaps the most familiar force we experience, and yet it is the most mysterious. From the moment we wake until we sleep, we feel it pulling us toward the earth, keeping our feet on the ground, making things fall. We're so accustomed to it that we forget to ask the simple question, what is it? What is this force really? Newton gave us an answer, a mathematical answer that worked beautifully for centuries. He said that every mass attracts every other mass with a force proportional to their masses and inversely proportional to the square of the distance between them. Elegant, yes, and useful. We could predict the motions of planets, the paths of cannonballs, the orbits of moons. The mathematics was impeccable. But there was something that bothered me, something that felt incomplete. Newton's gravity was instantaneous. If the sun suddenly disappeared, poof, gone, then according to Newton, Earth would immediately, instantaneously feel the change and fly off into space. But this troubled me because of what we learned about light, about information. Nothing can travel faster than light. Nothing can transmit information instantaneously. So how could gravity? And there was something else, something even more curious. Why does everything fall at the same rate? Drop a feather and a hammer on the moon, where there's no air resistance, and they hit the ground at the same moment. Galileo supposedly demonstrated this from the Leaning Tower of Pisa, though that story might be more legend than fact. But the principle is real, very real. Think about what this means. A heavy object and a light object. They accelerate downward at exactly the same rate. In Newton's framework, this is a coincidence, a remarkable coincidence. The gravitational force is stronger on the heavier object, but the heavier object is also harder to accelerate due to its greater inertia. These two effects exactly cancel out, always, perfectly, for every object. This seemed to me, it seemed too perfect to be coincidence. So I wondered for years, what if gravity isn't a force at all? What if instead it's something to do with the geometry of space itself? You see, when you're in an elevator and the cable snaps and you're in free fall, you don't feel gravity. You feel weightless. Things float around you. From your perspective, inside that falling elevator, it's as if gravity has been turned off. Or imagine the opposite. You're in a rocket in deep space, far from any planet or star, and the rocket accelerates upward. You'd feel pressed to the floor, exactly as if you were standing on Earth feeling gravity. From inside that rocket, you couldn't tell the difference between the rocket's acceleration and the pull of gravity. This equivalence, this deep equivalence between acceleration and gravity, it suggested something profound to me. Perhaps they are the same thing, viewed differently. Perhaps what we call gravity is actually the experience of living in curved space-time. Let me try to help you visualize this, though um, I must warn you that this is where words and everyday experience start to fail us. Imagine a rubber sheet stretched flat. This represents space, or rather, a two-dimensional slice of space to make it easier to picture. Now place a heavy ball, like a bowling ball, in the center. The sheet curves, dips down around the ball, yes? Now, if you roll a marble across this sheet, it won't travel in a straight line anymore. It will curve toward the bowling ball, not because the ball is pulling it with some mysterious force, but because the sheet itself is curved. The marble is actually trying to travel in a straight line, the straightest line possible, but in curved space. Straight lines are themselves curved. We call these paths geodesics. This is what massive objects do to space-time. The sun, with its enormous mass, curves the space around it. Earth isn't orbiting the sun because it's being pulled by some invisible force. No, no. Earth is simply following the straightest possible path through curved space-time. It's moving along a geodesic, and that geodesic happens to be an ellipse around the sun. The mathematics of this, the geometry, it's described by what we call the Einstein field equations. They're, they're beautiful in their structure, though I'll admit they can be quite complicated to work with. On one side of the equation, you have the curvature of space-time. On the other side, you have the distribution of matter and energy. Matter tells space-time how to curve, and curved space-time tells matter how to move. They're locked in this dance, this eternal conversation. Before we continue, I'd like to ask you to subscribe to the channel to help me reach the first 1,000 subscribers here. The purpose of this channel is to help you fall asleep with high quality knowledge, right? It doesn't cost anything. Just hit that subscribe button. Now, where was I? Yes, the consequences of curved space-time. Because if space can curve, then time must curve too, remember? Space and time are not separate, and this means that gravity affects time itself. Clocks run slower in stronger gravitational fields. Imagine two identical clocks. One you keep on the ground floor of a tall building, the other you place on the top floor. The one on the ground floor is deeper in Earth's gravitational field, where space-time is more curved. Time passes more slowly there, ever so slightly more slowly. The clock on the top floor ticks faster. How much faster? Well, for a building, even a very tall building, the difference is minuscule, perhaps 100 billionths of a second per day. But it's measurable with modern atomic clocks, and it's been measured. In 1971, two physicists, Haffele and Keating, took atomic clocks on commercial airline flights around the world. When they returned, the clocks showed exactly the time difference that general relativity predicted, both from their motion, that's special relativity, and from the changes in gravitational field as they flew at altitude, that's general relativity. This isn't just academic, you know. The GPS satellites orbiting Earth, they must account for both special and general relativity. They're moving fast, so their clocks run slow compared to Earth clocks. That's special relativity. But they're also higher up in a weaker gravitational field, so their clocks run fast compared to Earth clocks. That's general relativity. The second effect is actually larger. Without correcting for these relativistic effects, GPS would accumulate errors of several kilometers per day. Your phone's maps would be useless. So every time you use GPS to navigate, you're relying on general relativity being correct. You're relying on the fact that mass curves space-time and that time runs at different rates in different gravitational fields. It's rather wonderful when you think about it. This abstract theory, born from thought experiments about falling elevators and riding on light beams, now guides millions of people to their destinations every day. But perhaps the most striking prediction of general relativity is this. If matter curves spacetime, and if light follows the curvature of spacetime, then light itself should be bent by gravity. Starlight passing near the sun should be deflected, should appear to come from a slightly different position in the sky than it actually does. In 1919, Arthur Eddington led an expedition during a total solar eclipse. During the eclipse, when the sun's light was blocked by the moon, he could photograph stars that appeared near the sun in the sky, and he found that their positions were shifted, deflected by exactly the amount I had predicted 4 years earlier. It was a moment of validation, yes, but also of wonder. Light, which has no mass, is affected by gravity not because gravity pulls on it, but because gravity is the curvature of space-time itself. and light must follow that curvature. This bending of light leads to something extraordinary called gravitational lensing. If a massive galaxy or cluster of galaxies lies between us and a more distant galaxy, the light from that distant galaxy can be bent around the intervening mass, sometimes creating multiple images, sometimes creating rings of light. It's as if the universe has placed a magnifying glass in space, allowing us to see things we otherwise couldn't. The Hubble Space Telescope has captured remarkable images of this phenomenon. Distant galaxies, their light stretched and warped into arcs and rings by the gravity of galaxy clusters in the foreground. We use this effect now as a tool to study the distribution of matter in the universe, even matter we can't see directly, what we call dark matter. And here's something even stranger. If space-time can it curve enough to trap even light itself? If you compressed enough mass into a small enough volume, the curvature would become so extreme that nothing, not even light, could escape. The boundary beyond which nothing can escape, we call this the event horizon. And the object itself, we call it, well, John Wheeler gave it the name years later, a black hole. I had doubts about black holes, I must confess. They seemed too strange, too extreme. In 1939, I even wrote a paper arguing they couldn't form. But Karl Schwarzschild, while serving in the German army during the First World War, found a solution to my field equations describing exactly such an object, and later observations, decades later, showed that the universe is indeed full of these tiers in space-time. We've now detected black holes with masses millions or billions times that of our sun sitting at the centers of galaxies. We've observed stars orbiting around invisible points of mass, moving at incredible speeds. We've even just recently captured an image of the shadow of a black hole, the supermassive one at the center of the galaxy M87, using a network of radio telescopes spanning the Earth. And in 2015, something remarkable happened. A century after I wrote down the field equations, scientists detected gravitational waves for the first time. Two black holes, each about 30 times the mass of the sun, spiraled into each other and merged. This violent collision created ripples in space-time itself, waves of curvature that spread outward at the speed of light. By the time these waves reached Earth, they were incredibly weak, stretching and squeezing space by less than the width of a proton. But the LIGO detectors, with their laser beams traveling 4 kilometers back and forth, were sensitive enough to detect this whisper from across the universe. The universe is speaking to us in gravity now, not just in light. We can listen to the cosmos in a new way, hear the collisions of black holes and neutron stars, perhaps one day even the echo of the Big Bang itself. These gravitational waves, they carry information that light never could. When two black holes merge, no light escapes, nothing electromagnetic, but the space-time around them vibrates, rings like a bell struck by a hammer, and we can hear it now. Literally hear it because scientists converted those first detected waves into sound frequencies. It goes chirp, a rising tone as the black holes spiral faster and faster, then merge. A chirp from a billion light years away, from an event so violent it converted 3 solar masses worth of matter directly into gravitational radiation in a fraction of a second. 3 solar masses just gone, transformed entirely into ripples in space-time. And this brings me to something else, something perhaps even more fundamental than gravity itself: the relationship between matter and energy, between mass and what we might call the fabric of existence itself. You've probably seen the equation, yes? E equals mc squared. 3 symbols, 1 equal sign, perhaps the most famous equation in all of physics, and yet I think its true meaning is often missed, often simplified in a way that loses the profound strangeness of what it's actually telling us. People say energy equals mass times the speed of light squared, and they treat it like a conversion formula, like converting miles to kilometers. but it's saying something much deeper. It's saying that mass and energy are not different things at all. They are the same thing, the same substance, if you will, just in different forms. Mass is frozen energy. Energy is liberated mass. The distinction between them is, it's almost arbitrary, a matter of perspective and form. Think about what this means. Every object around you, everything with mass, the pillow beneath your head, your own body, the earth itself, all of it contains enormous, almost unimaginable amounts of energy. A single kilogram of matter, if you could convert it entirely to energy, would release about 90,000 trillion joules. That's roughly the energy of 21 megatons of TNT from 1 kilogram, the mass of a bag of sugar. Of course, we can't usually access this energy. Matter doesn't just spontaneously convert to energy under normal circumstances, thankfully for us. But in certain situations, it does happen. In the core of the sun, hydrogen nuclei fuse into helium, and in that process, a tiny amount of mass, less than 1%, is converted to energy. That tiny fraction powers all life on Earth, drives our weather, our oceans, our entire biosphere. The sunlight touching your face right now, it's mass that has been transformed, liberated from the prison of matter into the freedom of energy. In nuclear reactions, whether fusion in stars or fission in power plants, we see this principle at work. The products weigh slightly less than the reactants. That missing mass hasn't disappeared. It hasn't been destroyed. You cannot destroy mass energy. It's conserved always. It has simply changed form. It's become kinetic energy, heat, light, the energy that we can measure and use. And in matter-antimatter annihilation, we see it most completely. An electron meets a positron, its antimatter twin, and both vanish entirely, utterly, leaving nothing but a burst of gamma rays. 100% conversion, the ultimate liberation of bound energy. This equivalence between mass and energy, it came to me in 1905, that miraculous year when so many ideas fell into place. I was thinking about light again, about electromagnetic radiation, and I realized that if light carries energy, and if special relativity is correct about how energy transforms between reference frames, then, then there had to be this relationship. The mathematics demanded it. E equals mc squared emerged not from experiments with atoms or radiation, but from pure thought, from following the logical implications of relativity. And yet, here's what fascinates me. I didn't fully understand at the time what this would mean for the universe, for cosmology, for the large scale structure of everything. That came later when I tried to apply general relativity to the universe as a whole. You see, in the early part of the last century, most astronomers believed the universe was static, unchanging. Yes, stars moved, planets orbited, but the overall structure, the cosmos itself, was thought to be eternal and fixed. When I applied my field equations to the universe as a whole in 1917, I found something disturbing. The universe couldn't be static. Gravity would cause it to collapse in on itself. Everything would fall together. This bothered me greatly. I believed, like everyone else, that the universe must be stable, unchanging on the largest scales. So I did something that, well, I later called it my greatest blunder. I added a term to the equations, a cosmological constant, a kind of repulsive force that would exactly balance gravity and keep the universe static. Mathematically, it worked. The equations allowed it, but it was artificial, added only to achieve a preconceived result. And then, about a decade later, Edwin Hubble made his observations. Using the 100-inch telescope on Mount Wilson, he observed distant galaxies and found something extraordinary. They were all moving away from us. The farther away they were, the faster they were receding. The universe wasn't static at all. It was expanding. Space itself was growing, carrying galaxies apart like raisins in rising bread dough. The galaxies weren't moving through space, space itself was expanding between them, and if you run this expansion backward in time, you arrive at a point where everything was together, compressed into an infinitely dense, infinitely hot state. The beginning, what we now call the Big Bang. I had missed it. The equations were telling us the universe must be dynamic, either expanding or contracting, and I had refused to believe it, forcing them to be static with my cosmological constant. If I had trusted the mathematics, trusted where the equations led instead of my intuition, I might have predicted the expansion of the universe. Instead, others did. But here's the curious thing, the twist in the story, that cosmological constant I added and later rejected. It seems the universe actually has something like it after all. In 1998, observations of distant supernovae showed that the expansion of the universe isn't just continuing, it's accelerating. Galaxies are being pushed apart by something, some energy inherent in space itself. We call it dark energy, and it behaves very much like a cosmological constant. So perhaps my greatest blunder wasn't such a blunder after all. Or perhaps it was a blunder in application, but not in conception. The universe is strange enough to include such things. This accelerating expansion, though, it raises profound questions. What is this dark energy? It seems to make up about 68% of the universe's total energy content. Dark matter, that invisible mass we detect only through its gravitational effects, makes up another 27%. And ordinary matter, the stuff of stars and planets and us, barely 5%. We are quite literally a tiny minority in the universe, made of the rarest substance there is. The cosmological implications keep unfolding, you see. We now know the universe is about 13.8 billion years old. We can trace its history back to fractions of a second after the Big Bang. We understand, or we think we understand, how the first atoms formed when the universe was a few minutes old, how the first stars ignited hundreds of millions of years later, how galaxies assembled and evolved. But there are mysteries still, deep mysteries. What happened at the very first instant? The equations break down at the moment of the Big Bang itself. Quantum mechanics tells us that at extremely small scales and high energies, space and time themselves might become uncertain, fluctuating. We need a theory that unifies general relativity with quantum mechanics, and we don't have one yet, not a complete one. String theory tries, loop quantum gravity tries, others try. But we haven't found the answer, the framework that describes both the very large and the very small, both gravity and the quantum realm, in one coherent picture. What we do know is that the universe is far stranger, far more wonderful than anyone imagined even 100 years ago. It began in fire, it expands into darkness, it's governed by principles that seem impossible, yet are demonstrably true. Time flows differently depending on speed and gravity. Mass and energy are interchangeable. Space itself curves and ripples. And perhaps, strangest of all, consciousness has emerged within this universe, matter that can contemplate its own existence, ask questions about its origins. We measure things, don't we? We observe, we record, we try to understand what is happening in the world around us. It seems like such an innocent activity, such a passive thing. You look at something, you measure it, you learn about it. The thing you're observing goes about its business, unchanged by your watching. A tree doesn't care if you measure its height. The moon doesn't mind if you observe its orbit. But at the smallest scales of reality, at the level of atoms and particles, something very strange happens. The act of measurement itself, the act of observation, it changes what you're measuring. Not because you're clumsy, not because your instruments disturb things, though they do, but because of something more fundamental, something that goes to the very heart of what reality is. This is the quantum world, and I must tell you, It troubled me deeply. Still troubles me, if I'm being honest, because in the quantum realm nothing is certain until you look at it. And I spent much of my later years arguing that this couldn't be the final answer, that there must be something deeper, something more complete. But the universe, as far as we can tell, really does work this way. Let me take you back to the early part of the 20th century. Physics was in crisis, you see, a beautiful crisis. Classical physics, Newton's mechanics, Maxwell's electromagnetism, they worked magnificently for describing the world we could see and touch. But when physicists began studying the behavior of light and atoms, things stopped making sense. Light behaved like a wave, it created interference patterns, it diffracted around obstacles, it did all the things waves do. But in 1905, the same year I developed special relativity, I published another paper about something called the photoelectric effect. When you shine light on certain metals, electrons are ejected. But here's the strange part. The energy of those electrons doesn't depend on the brightness of the light. It depends on the color, the frequency. If light were purely a wave, brighter light should eject electrons with more energy, but it doesn't. Instead, blue light, even very dim blue light, can eject electrons while bright red light cannot, no matter how intense you make it. This only makes sense if light comes in discrete packets, little bundles of energy. I called them light quanta. Others later called them photons. So light is both wave and particle. Which is it really? The answer, the frustrating, wonderful answer, is that it's both, or neither, or or the question itself is wrong based on classical intuitions that don't apply at this scale. Light is what it is, and it exhibits wave-like properties in some experiments and particle-like properties in others. We simply don't have everyday words for what it truly is. And then it got stranger. If light, which we thought was a wave, acts like particles, what about electrons? We knew electrons were particles, little bits of matter with mass and charge, but in the 1920s, Louis de Broglie proposed something audacious. Maybe electrons have wave properties too. Maybe all matter does. And when experiments were done, firing electrons through narrow slits, they created interference patterns. Interference patterns, just like light waves do. Individual electrons, particles of matter, somehow interfering with themselves as if each electron goes through multiple paths simultaneously, like a wave spread out in space. This wave-particle duality, it's not a metaphor. It's not that particles are kind of like waves sometimes. At the quantum level, the distinction between particle and wave simply doesn't exist in the way we imagine it should. Things are described by wave functions, mathematical entities that spread out in space, that can interfere and superpose, and only when you measure them do you find the particle in a definite location. Werner Heisenberg discovered something else, something equally disturbing to our classical intuitions. There's a fundamental limit to how precisely you can know certain pairs of properties simultaneously. The more precisely you know a particle's position, the less precisely you can know its momentum, its velocity. This isn't a limitation of our instruments. It's a limitation of reality itself. The universe, at its smallest scales, is inherently fuzzy, probabilistic. You cannot know everything about a quantum system, not because you haven't measured carefully enough, but because there isn't a definite everything to know. The particle doesn't have a precise position and momentum simultaneously. These properties only become definite when measured. I couldn't accept this. I thought it must mean our theory was incomplete, that there were hidden variables, deeper deterministic laws we hadn't discovered yet. I debated this with Niels Bohr for years. God does not play dice with the universe, I famously said. And Bohr replied, something like, stop telling God what to do. We devised thought experiments, paradoxes, to show that quantum mechanics must be incomplete. The most famous is what's now called the EPR paradox, after myself, Boris Podolsky, and Nathan Rosen. We imagine two particles that interact and then fly apart. According to quantum mechanics, they remain connected, entangled in a way that transcends space. Measure something about one particle, and you instantly know something about the other, even if they're light years apart. This seemed to violate special relativity, to require faster than light communication. We thought this proved quantum mechanics must be wrong, or at least incomplete. There must be hidden information, predetermined values that the particles carry with them. But in the 1960s, John Bell figured out a way to test this. He derived inequalities, mathematical relationships that must hold if there are local hidden variables, if the particles carry predetermined information. And when experiments were done again and again, Bell's inequalities were violated. Quantum mechanics was right. The entanglement is real. Two particles can be connected in a way that transcends space, not because information travels between them faster than light. It doesn't. You can't use entanglement to send messages, but because they're not truly separate. They're part of one quantum system, one wave function, no matter how far apart they are in space. Measuring one instantaneously affects what you'll find when measuring the other, not because a signal travels between them, but because the question, what are the properties of this individual particle, doesn't have a definite answer until measurement collapses the combined wave function. It's as if reality itself is non-local at the quantum level. Space doesn't separate things in the way we intuitively think it should. The universe is more deeply interconnected, more holistic than classical physics ever imagined. This still bothers me, even now, even knowing the experiments confirm it. It suggests that either locality is wrong, things that are far apart can influence each other instantly, or realism is wrong, the idea that objects have definite properties independent of observation, or both. Quantum mechanics forces us to give up something we thought was fundamental about reality, and then there's the measurement problem. What happens during that collapse of the wave function? Before you measure an electron's position, it's described by a wave function spread out in space, existing in a superposition of many possible locations. When you measure it, you find it in one specific place. The wave function collapses. But what counts as a measurement? Where does the quantum world end and the classical world begin? Schrödinger, trying to show how absurd he thought this was, imagined a cat in a box with a quantum random device that might or might not kill the cat. Until you open the box, is the cat in a superposition of alive and dead? Of course not, right? And yet, where do you draw the line? Some interpretations say consciousness causes collapse. Some say the universe constantly splits into multiple branches, and all outcomes actually happen in different parallel worlds. Some say there is no collapse at all, just quantum correlations spreading outward. We don't know. We genuinely don't know what measurement means, what consciousness is, whether reality exists independent of observation. What we do know is that quantum mechanics works perfectly. Every prediction it makes, every experiment we perform confirms it. Transistors, lasers, computers, MRI machines, all of modern technology rests on quantum principles. We've learned to manipulate individual atoms to create quantum computers that exploit superposition and entanglement. The universe reveals itself in layers, you see, each stranger than the last. The classical world of Newton, deterministic and mechanical. The relativistic world where space and time merge and curve. The quantum world where reality is probabilistic and non-local. And we don't yet know if there are deeper layers still, whether space and time themselves might be emergent from something more fundamental. What holds things together? Have you ever wondered this, lying in bed at night? What keeps the nucleus of an atom from flying apart when all those positively charged protons should be repelling each other with tremendous force? What binds quarks into protons and neutrons? Why does matter have the structure it has with atoms and molecules and crystals rather than just dispersing into nothingness? There are forces at work, you see, forces beyond gravity and electromagnetism, forces that only operate at the tiniest scales within the atomic nucleus. And understanding these forces, understanding how all the forces of nature might be related, might be different aspects of one underlying principle. This was a dream that occupied much of my later life, a dream I never fulfilled, but one that physicists still pursue today. Let me tell you about the strong force, this remarkable interaction that holds atomic nuclei together. It's the strongest of all the fundamental forces, about 100 times stronger than electromagnetism at close range. But it has a peculiar property. It only works over incredibly short distances, distances comparable to the size of a nucleus, about a femtometer. That's 10 to the minus 15 meters, a millionth of a billionth of a meter. Outside this range, the strong force essentially vanishes. It's as if nature has installed a switch that turns off completely beyond a certain distance. This is very different from gravity or electromagnetism, which decrease with distance but never truly disappear. You can feel the sun's gravity from Earth, 93 million miles away. But the strong force holding together the nucleus of an atom in your body, it doesn't extend even to the next atom over. This short range is why we can have stable atoms at all, why chemistry works the way it does. If the strong force reached across larger distances, all matter would stick together inseparably. But confine it to the nucleus, and you have the foundation for the rich complexity of chemistry, of molecular structures, of life itself. Then there's the weak force, even more peculiar. It's responsible for certain types of radioactive decay, for the process that allows the sun to shine by converting protons into neutrons in its core. Without the weak force, the sun would be dark, fusion couldn't proceed, and we wouldn't exist. Yet it's called weak because, well, because it is weak, much weaker than electromagnetism or the strong force, and its range is even shorter, operating only over distances about 1,000th the size of a proton. So we have four fundamental forces: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. Four different interactions governing everything that happens in the universe. But surely there must be some deeper unity, some way to understand them all as manifestations of a single underlying principle? James Clerk Maxwell did this for electricity and magnetism in the 1860s. Before him, these were thought to be separate phenomena. Electric charges create electric fields, magnets create magnetic fields, different things. But Maxwell showed they're inseparable, two aspects of one electromagnetic force. A changing electric field creates a magnetic field. A changing magnetic field creates an electric field. They're coupled, intertwined aspects of a unified electromagnetic interaction. This unification was beautiful, and it was powerful. From Maxwell's equations, the speed of light emerges naturally as a consequence of the properties of electric and magnetic fields. Light itself is revealed as an electromagnetic wave, electricity and magnetism dancing together through space. Could we do something similar for all the forces? This became my quest, particularly trying to unify electromagnetism with gravity. I spent decades on this, trying different mathematical approaches, different geometries. I published papers, explored possibilities, but I never found it, never achieved that grand unification. Others continued where I left off. In the 1960s and 70s, physicists discovered something remarkable. They could unify electromagnetism and the weak force. At high enough energies, energies that existed in the early universe, these two forces become one, the electroweak force. It's only at lower energies, the energies we experience in everyday life, that this symmetry breaks and they appear as separate forces. This was profound, you see, because it suggested that in the beginning, in the incredibly hot, dense moments after the Big Bang, the forces of nature might have been unified. As the universe cooled and expanded, symmetries broke, and the forces separated, took on their distinct characters. Like water freezing into ice, where the liquid's symmetry gives way to the crystalline structure's preferred directions. And there are hints, mathematical hints, that at even higher energies, the strong force might join this unification. The electromagnetic, weak, and strong forces might all be aspects of one grand unified force. Some theories predict this should happen at energies about a trillion times higher than what we can achieve in our most powerful particle accelerators. We can't test this directly, can't recreate such energies, but we can look for consequences, for subtle effects that might show up at lower energies. So far, um, we haven't found conclusive evidence, but the mathematical elegance of these theories is compelling. And gravity? Gravity remains stubbornly separate. It's described by general relativity, by curved spacetime, while the other forces are described by quantum field theory. These are different languages, different frameworks. String theory attempts to bridge this gap by proposing that fundamental particles aren't point-like, but are actually tiny vibrating strings. Different vibration modes correspond to different particles, and one particular vibration mode corresponds to the graviton, the hypothetical particle that would carry the gravitational force. String theory has its own elegance, its own mathematical beauty. It requires extra dimensions of space beyond the three we experience, dimensions curled up so small we can't detect them. It makes predictions about quantum gravity, about black holes, about the very structure of spacetime at the Planck scale, 10 to the minus 35 meters, where both quantum effects and gravitational effects become equally important. But we can't test it, not directly. The energies required are far beyond anything we can produce. And there are many versions of string theory, many ways to compactify those extra dimensions, leading to different predictions about what we should observe. It's a theory still searching for experimental validation, still mathematical music waiting to find out if nature plays this particular tune. What troubles me about all these unification attempts is something I felt even in my own efforts. We're guided by mathematical beauty, by elegance, by what feels right to our aesthetic sense. But is nature obligated to be elegant in the way we define elegance? Does the universe care about our sense of beauty? History suggests that nature does often choose the mathematically beautiful solution. Maxwell's equations are beautiful. General relativity is beautiful. Quantum mechanics, for all its interpretational difficulties, has a mathematical structure that is remarkably elegant. There seems to be a deep connection between mathematical truth and physical truth, between what is beautiful and what is real. But why? Why should the universe be comprehensible through mathematics at all? Why should abstract symbols on paper correspond to the behavior of distant galaxies and tiny particles? This is to me one of the great mysteries, perhaps the greatest mystery. The universe didn't have to be this way. It could have been chaotic, lawless, impossible to describe with equations. But it isn't. It follows rules, and those rules can be written in the language of mathematics. Eugene Wagner called this the unreasonable effectiveness of mathematics in the natural sciences. And he was right to find it unreasonable, mysterious. We invent mathematical structures to describe patterns we observe, and then we find those structures predicting phenomena we haven't observed yet, couldn't have imagined. Dirac's equation predicted antimatter before anyone knew antimatter existed. Maxwell's equations predicted electromagnetic waves before anyone had detected radio waves. My equations predicted gravitational waves and black holes and the bending of starlight. The mathematics seems to know things about the universe that we don't, seems to lead us to discoveries we couldn't have made through experiment alone. It's as if we're discovering the universe through pure thought, through following logical implications of mathematical structures. And then when we look at the universe, there it is, behaving just as the mathematics predicted. This suggests something profound about the relationship between mind and cosmos, between thought and reality. Are we discovering mathematical truths that exist independently, platonically, eternally? Or are we inventing structures that happen to match reality for reasons we don't understand? Is mathematics the language the universe is written in, or is it just a tool that happens to work? I don't have answers to these questions, only wonder. Only this sense that we're touching something deep here, something about the nature of existence itself. But how do we know? And this is the question, isn't it? How do we know that any of these beautiful mathematical structures, these elegant theories, actually describe reality? Science is not philosophy, not pure mathematics, not theology. Science must make predictions, must expose itself to the possibility of being wrong, a theory that explains everything, that can accommodate any observation, actually explains nothing. I've always believed, I've always felt that imagination is more important than knowledge. Yes, this is true, but imagination without the discipline of experimental verification, without the harsh test of reality, it becomes mere fantasy. Beautiful, perhaps, internally consistent, perhaps, but disconnected from the world. When I proposed that light should bend around the sun, this wasn't just an abstract idea. It was a prediction, a specific prediction. Starlight passing near the sun during an eclipse should shift by a particular amount, 1.75 arcseconds for light grazing the sun's surface. Newton's theory predicted about half that, 0.875 arcseconds. So here was a test, a clear distinction between two theories. Eddington's expedition in 1919, measuring star positions during the solar eclipse. This was crucial, not because the mathematics needed confirmation for me. I was quite confident in the mathematics, but because the universe didn't have to obey my mathematics. Reality is under no obligation to be described by general relativity or any other human theory. The eclipse measurement was asking the universe, is this how you actually work? And the universe answered yes. This is humbling, you see. We can create the most beautiful theories, the most compelling arguments, but in the end, nature decides. Nature is the final arbiter, and nature has surprised us again and again, shown us that reality is stranger than we imagined. Take the perihelion of Mercury, the slow rotation of its orbit around the sun. Newton's theory couldn't quite account for it. There was a tiny discrepancy, just 43 arcseconds per century. Some astronomers thought there must be another planet closer to the sun perturbing Mercury's orbit. They even gave it a name, Vulcan. But Vulcan was never found because it doesn't exist. When I applied general relativity to Mercury's orbit, that discrepancy disappeared. The calculation gave exactly the observed value. I remember when I realized this in November 1915, I had heart palpitations. I felt something like a rupture in my thinking. The theory explained this anomaly naturally, without inventing new planets, without adding anything artificial. It just worked. This is what we look for in physics, this explanatory power. A theory that not only predicts new phenomena, but also explains existing puzzles, anomalies that didn't fit the old framework. It's like finding a key that fits a lock you didn't even know was there. But verification is not a one-time thing. We must test theories again and again, in different ways under different conditions. General relativity has now been tested to extraordinary precision. The Gravity Probe B satellite measured how Earth's rotation drags space-time around it, an effect called frame dragging. The measurements match the predictions to better than 1%. GPS satellites, as I mentioned, depend on relativistic corrections every moment. The binary pulsar discovered by Hulse and Taylor, two neutron stars orbiting each other, is losing energy exactly as general relativity predicts it should through gravitational wave emission. They're spiraling toward each other, and we can measure this, can watch the theory's predictions unfold over decades of observation. Each test could have falsified the theory. Each time we look more precisely, we might find a deviation, a hint that general relativity is not quite right, that there's something deeper, and maybe someday we will. No theory is final, you see. Newton's theory worked magnificently for centuries before we found its limitations. My theory, too, might have a domain beyond which it breaks down, situations where something else takes over. This is how science progresses, through this dialogue between theory and experiment, between imagination and verification. We propose, nature disposes. We ask questions, and sometimes, the universe answers in ways we can understand. And what has the universe told us about time? Not just how it dilates and curves, but about its direction, its arrow. Why does time flow from past to future? Why do we remember yesterday but not tomorrow? Why do eggs break but never spontaneously reassemble? Why does coffee cool but never spontaneously heat up? This brings us to something called entropy, a concept from thermodynamics. Rudolf Clausius formulated it in the mid 1800s. Entropy it's a measure of disorder, of the number of ways a system can be arranged. And the second law of thermodynamics says that entropy always increases, or at best stays the same. Things become more disordered over time, never less disordered spontaneously. A broken egg has higher entropy than an intact egg because there are many more ways to arrange the pieces of a broken egg than to arrange an intact one. Once broken, the molecules don't spontaneously reorganize themselves. The probability is not zero, mind you, but it's so vanishingly small that it effectively never happens. This second law, it gives time its direction. Physical laws themselves, whether Newton's or mine, they're time symmetric. The equations work equally well running forward or backward in time. If you film planets orbiting and play the film backward, the backward motion still obeys the laws of physics. But entropy is different. Entropy increases in only one direction, defines a forward direction for time. Ludwig Boltzmann understood this microscopically. Entropy is related to probability, to the number of microscopic states corresponding to a macroscopic condition. High entropy states are simply more probable, because there are more ways to arrange things in a disordered way than in an ordered way. But this raises a profound question. If entropy always increases, if the universe is always becoming more disordered, then in the past, it must have been more ordered. And if we trace back far enough to the beginning, the Big Bang, the universe must have been in an extraordinarily low entropy state, extremely ordered, despite being incredibly hot and dense. Why? Why did the universe begin in such a special state? This is not explained by the Big Bang theory itself. It's an initial condition, we must assume, a boundary condition at the beginning of time. And it's a very specific, very unlikely condition. If the early universe had been in a typical high entropy state, it would have been essentially featureless, in thermal equilibrium, and nothing interesting would have happened. No structure would have formed, no galaxies, no stars, no us. So the fact that we exist, that there's complexity and structure in the universe, it traces back to this low entropy beginning. But we don't know why the universe began that way. Some think it might be related to gravity, to the fact that gravity is always attractive and creates structure. Others think it might require understanding what happened before the Big Bang, if such a phrase even makes sense. And what about the future? If entropy keeps increasing, where does that lead? To what we call the heat death of the universe. Eventually, in the far, far future, trillions upon trillions of years from now, all useful energy will be dispersed. Stars will burn out, black holes will evaporate through Hawking radiation, and everything will approach a uniform maximum entropy state. No gradients, no flow of energy, no possibility of complex structures or processes, just equilibrium, silence. This seems bleak, doesn't it? The universe grinding down to darkness and uniformity. But this is so far in the future, such vast timescales that I find it hard to feel troubled by it. Humanity might evolve into something unrecognizable, might spread across the cosmos, might discover ways of existing we can't yet imagine, or we might be long gone. Either way, we have time, enormous amounts of time. What concerns me more is the present, the now, what we do with the brief moment of low entropy we find ourselves in, this ordered state, this temporary island of complexity in the ocean of entropy. It's precious. Life itself is a fight against entropy, a local decrease in disorder maintained by consuming energy, by increasing entropy elsewhere. We are patterns in the chaos, structures sustained by flow, by the sun's energy streaming through us and radiating away as heat. We exist because of entropy's increase, because energy flows from hot to cold, from order to disorder, and in that flow, briefly, wonderfully, there can be life, consciousness, thought. Life is such an improbable thing when you really think about it. Not impossible, clearly. We're here after all, but improbable. So many things had to be just right, just so. The temperature of our planet, the composition of the atmosphere, the presence of liquid water, the protective magnetic field, the stable sun, the moon stabilizing Earth's tilt. Any one of these factors slightly different, and life as we know it might never have emerged. And it's not just Earth. The laws of physics themselves, the fundamental constants that govern how the universe works, they seem remarkably fine-tuned for the existence of complexity, of structure, of life. Change any of these constants by even a small amount, and the universe becomes inhospitable, barren. Consider the strength of gravity, for instance. If gravity were just slightly stronger, stars would burn through their fuel too quickly, collapsing before planets could form, before life could evolve. If it were slightly weaker, stars might never ignite at all, never achieve the temperatures and pressures needed for nuclear fusion. The universe would be cold, dark, nothing but clouds of hydrogen drifting forever. Or think about the strong nuclear force, the one holding atomic nuclei together. If it were just 2% stronger, protons would bind together so readily that all the hydrogen in the early universe would have fused into heavier elements. No hydrogen left means no water, no organic chemistry as we know it. If the strong force were slightly weaker, nuclei wouldn't be stable enough to form anything beyond hydrogen. No carbon, no oxygen, no building blocks for complexity. The electromagnetic force, if it were different in strength, atoms would have different properties, chemistry would work differently, if at all. The masses of fundamental particles, quarks and electrons, if these were slightly different, stable atoms couldn't exist. The list goes on, you see, many parameters that seem precisely calibrated for a universe that can host complexity. Some call this the fine-tuning problem. Why are the constants what they are? Why this particular set of values and not others? There are several ways to think about this puzzle, and none of them are entirely satisfying, I must admit. One response is to say, of course, the universe appears fine-tuned for life. If it weren't, we wouldn't be here to observe it. This is called the anthropic principle. We can only observe a universe compatible with our existence. It's a selection effect, in a way, like a fish being amazed at how perfectly suited the ocean is for swimming, never considering all the places that have no water at all. But does this really explain anything? It feels somewhat circular, doesn't it? Why is the universe this way? Because otherwise we couldn't ask the question. It's true, certainly true, but it doesn't tell us why this universe exists rather than some other configuration. Some physicists and cosmologists have proposed the multiverse as an answer. Perhaps our universe is just one of countless universes, each with different physical laws, different constants. In most of these universes, conditions aren't suitable for life. But in a vast enough multiverse, in an infinite ensemble of possibilities, some universes by chance will have the right properties. We find ourselves in one of those well, because we couldn't find ourselves anywhere else. This idea has some theoretical support. Certain versions of string theory suggest a vast landscape of possible universes, something like 10 to the 500th different vacuum states, each corresponding to different low energy physics, different effective laws, cosmic inflation, a theory about the very early universe in some formulations naturally produces multiple bubble universes, each potentially with different properties. But the multiverse it's troubling from a scientific perspective. If these other universes are truly separate, if there's no way to observe them or interact with them, can we really call this science? Are we not crossing into metaphysics, into untestable speculation? A theory that explains our universe by postulating infinitely many unobservable universes. This seems to lose something essential, some connection to the principle of verification I hold dear. And yet, perhaps we're being too narrow in our definition of what's testable. If a theory makes multiple predictions and all the other predictions check out, does that lend credibility to the predictions we can't directly test? If inflation explains the uniformity of the cosmic microwave background, explains the flatness of space, explains the spectrum of density fluctuations, and as a consequence also predicts a multiverse, do we accept the whole package? I'm not sure. I genuinely don't know. But I find it remarkable that asking why the universe is suitable for life leads us to these profound questions about the nature of reality itself, about what lies beyond our observable horizon. There's another possibility, though, one that some find appealing. Perhaps the constants aren't really constant. Perhaps they evolved, in some sense, perhaps through a process analogous to natural selection. Lee Smolin proposed an idea called cosmological natural selection, where new universes might be born inside black holes, inheriting slightly modified physical laws from their parent universe. Universes that produce many black holes would have more offspring, and if the conditions for black hole formation happen to overlap with conditions suitable for complexity and life, well, then we might expect to find ourselves in such a universe. It's speculative, very speculative, but it has the appeal of making our universe less of an improbable accident and more of an inevitable outcome of some deeper process. Though um, I must say it still requires something to start the process, some universe or meta law that allows this evolution to occur. What strikes me about all these discussions is how they push us toward questions that physics alone cannot answer. Why is there something rather than nothing? Why these laws rather than other laws? Why is mathematics effective? Why does consciousness exist? These questions sit at the boundary between physics and philosophy, and perhaps they always will. Some of my colleagues wanted me to make statements about God, about religion, about whether physics leaves room for the divine. I was always careful about this, tried to be clear about what physics can and cannot tell us. Physics describes how the universe works, the patterns and regularities we observe. It doesn't tell us why there is a universe at all, doesn't address questions of meaning or purpose. I've said that science without religion is lame, religion without science is blind. What I meant was that we need both the empirical discipline of science and the moral, spiritual dimension that gives life meaning. They address different questions, different aspects of human experience. Science tells us what is, ethics and spirituality tell us what ought to be, what matters, how to live. When I used the word God, I usually meant something more like Spinoza's God, the order and harmony of the universe itself, the elegant mathematical structure underlying reality. Not a personal God who intervenes in human affairs, who answers prayers or performs miracles. The feeling of awe and wonder at the cosmos, at the fact that it's comprehensible, that simple equations describe vast phenomena, this is religious in a sense, a cosmic religious feeling, but it's not conventional religion. I respect deeply those who find comfort and meaning in traditional faith. Who am I to say their experience isn't valid? But I couldn't convince myself to believe in a God who concerns himself with the daily affairs of humans, who rewards or punishes, who requires worship. The universe is too vast, too old, too filled with suffering and beauty both, for such anthropocentric notions to make sense to me. What I do believe, what I feel in my bones, is that there is something extraordinary about existence itself. The fact that we are here, conscious matter contemplating its own nature, asking questions about the cosmos, this is profound beyond words. We are a way for the universe to know itself, as someone said. Hydrogen atoms, given enough time, become conscious, begin to wonder about their origins. And perhaps that's enough. Perhaps the meaning of life is not something imposed from outside, but something we create, we discover through the act of living, of questioning, of connecting with others, of trying to understand and appreciate this strange, beautiful universe we find ourselves in. The constants may or may not be fine-tuned by design. The multiverse may or may not exist. God, however you define the term, may or may not be watching. But what's certain, what we know with confidence, is that we are here now, part of an unfolding cosmic story that began 13.8 billion years ago and continues in ways we can barely imagine. When we look up at the night sky, what are we really seeing? Points of light, yes, scattered across the darkness, some brighter, some dimmer. If you watch long enough, you notice they move in patterns, predictable patterns. The ancients mapped these movements, created stories around them, saw gods and heroes in the configurations. But we know now what those points of light really are. They are stars, suns like our own, some larger, some smaller, burning through nuclear fusion, converting hydrogen to helium and heavier elements. And the light we see, it didn't leave those stars just now. It left years ago, centuries ago, sometimes thousands of years ago. We are not seeing the stars as they are, but as they were, looking backward in time with every photon that reaches our eyes. The nearest star beyond our sun, Proxima Centauri, is about 4 light years away. When you see its light tonight, you're seeing light that left that star 4 years ago. If Proxima Centauri exploded yesterday, we wouldn't know for another 4 years. The information cannot reach us faster than light can carry it. And that's one of the nearest stars. Most stars you can see with the naked eye are hundreds or thousands of light years distant. The Andromeda Galaxy, that fuzzy patch visible on dark nights, is 2.5 million light years away. The light entering your eye left Andromeda before humans existed, when our ancestors were still ape-like creatures in Africa. This means when we look at the universe, we're looking at history, at a three-dimensional temporal map. The farther away something is, the farther back in time we're seeing it. And this gives us a remarkable ability. We can observe the universe at different epochs, see how it has evolved, how galaxies formed and changed over billions of years. The most distant objects we can see, quasars and galaxies detected by powerful telescopes like the James Webb Space Telescope, they're so far away that their light has been traveling toward us for more than 13 billion years. We're seeing them as they were when the universe was young, less than 1 billion years after the Big Bang. We're looking into the cosmic dawn, the era when the first stars were igniting, when galaxies were just beginning to assemble. But there's a limit, you see, a horizon beyond which we cannot see, not because our telescopes aren't powerful enough, but because light hasn't had time to reach us yet. The universe is 13.8 billion years old, and light travels at a finite speed. So the most distant light that could possibly reach us comes from objects whose light has been traveling for, well, for all that time. Actually, it's a bit more complicated because the universe has been expanding while that light travels. Space itself stretches, carrying distant objects farther away and stretching the wavelengths of light in the process. We call this cosmological redshift. Light that left a distant galaxy as ultraviolet might arrive at Earth as infrared, its wavelength stretched by the expansion of space between emission and reception. The most distant thing we can see is not a galaxy or star, but the cosmic microwave background radiation, the afterglow of the Big Bang itself. When the universe was about 380,000 years old, it cooled enough for electrons and protons to combine into neutral hydrogen atoms. Before this moment, the universe was opaque, filled with a plasma of charged particles that scattered light continuously. But once atoms formed, light could travel freely. The universe became transparent. That light has been traveling ever since, stretched and cooled by the expansion, arriving at Earth now as microwave radiation, corresponding to a temperature of about 2.7 degrees above absolute zero. We detect it coming from all directions, a nearly uniform glow filling the entire sky. This radiation, it's a baby picture of the universe, a snapshot from when it was just a tiny fraction of its current age. And remarkably, the cosmic microwave background is not perfectly uniform. There are tiny variations, tiny fluctuations in temperature, about 1 part in 100,000. These ripples, these tiny density variations in the early universe, they were the seeds from which all structure grew. Regions slightly denser than average had slightly stronger gravity, pulled in more matter, became denser still. Over millions and billions of years, these tiny ripples grew into the galaxies and galaxy clusters we see today. We can map these fluctuations with satellites like COBE, WMAP, and Planck. The resulting maps they're beautiful, they're profound. They encode information about the geometry of space, the composition of the universe, the nature of the initial conditions. From these maps, we've determined that space is flat, or very nearly flat, on large scales. We've measured the amounts of ordinary matter, and dark energy. We've even detected hints of gravitational waves from the inflationary epoch, though that result is still being debated. The cosmic microwave background represents a horizon in time. We cannot see directly beyond it, cannot observe the universe when it was younger than 380,000 years, because before that moment, light couldn't travel freely. But we can infer what happened, can reconstruct those first moments through physics, through understanding how matter and radiation behave at extreme temperatures and densities. In the first second after the Big Bang, the universe was unimaginably hot and dense. Temperatures were high enough that not even atomic nuclei could exist. Matter was broken down into its most fundamental constituents, quarks and gluons, existing in a state called a quark-gluon plasma. We've actually created this state briefly in particle accelerators, smashing heavy nuclei together at nearly light speed, recreating for microseconds the conditions that filled the universe in its first moments. As the universe expanded and cooled, quarks combined into protons and neutrons. When it was about 1 second old, conditions were right for nuclear fusion to begin. Protons and neutrons fused into deuterium, then helium, and small amounts of lithium. This process, called Big Bang nucleosynthesis, lasted only a few minutes. After that, the universe was too cool and diffuse for fusion to continue. We can calculate what proportions of these light elements should have been produced, and when we look at the universe at the most pristine gas clouds we can find, gas that hasn't been contaminated by material from stars, the abundances match. About 75% hydrogen, 25% helium by mass, trace amounts of deuterium and lithium. The universe is stamped with the signature of its birth. Every helium atom in your body, in fact, was mostly created in those first few minutes. The hydrogen is even older. Protons are essentially unchanged since the first second. When you breathe, you're breathing atoms that are almost as old as time itself, processed through countless stars, perhaps, but fundamentally ancient, primordial. And what about before that first second? What happened at the very beginning, at time zero? Here the physics becomes uncertain, speculative. We know the universe was extremely hot and dense, but as we approach the Planck time, 10 to the minus 43 seconds after the beginning, quantum gravitational effects become important. Space-time itself becomes quantum, fluctuating, uncertain. Our theories break down. We simply don't know what, if anything, it means to talk about time before this point. Some theories suggest the Big Bang might not have been the absolute beginning, but rather a transition from some previous state. The universe might have been contracting before, bounced, and then began expanding. Or it might have emerged from quantum fluctuations from nothing, though nothing in quantum mechanics is never truly nothing, always seething with virtual particles and fields. Or perhaps time itself began at the Big Bang, and the question, what came before, is meaningless, like asking what's north of the North Pole. Time, as we understand it, might be a property of our universe that didn't exist before our universe existed. These are deep waters, you see, where physics and philosophy and mathematics all merge together, where we're pushing against the boundaries of what we can know, what we can even meaningfully ask. But this is what draws us forward, isn't it? Not the answers we have, but the questions we can barely formulate, the mysteries that linger just beyond our current understanding. The universe reveals itself slowly, grudgingly, and each answer opens up new questions, deeper mysteries. We are children learning to read a book written in a language we're only beginning to understand, a book whose final chapters may forever remain unreadable. You know what puzzles me greatly? It's not just that we exist, but that we know we exist. Consciousness, this strange property of matter organized in certain ways, this ability to reflect, to wonder, to ask questions about itself. A brain, which is just atoms, just electrons moving through neural pathways, somehow gives rise to subjective experience, to the feeling of being someone, of experiencing red or pain or joy or curiosity. How does this happen? How do unconscious particles, following physical laws, arranging themselves into certain patterns, suddenly become aware? There is what philosophers call the hard problem of consciousness, explaining not just how brains process information, which we're making progress on, but how and why there is something it feels like to be us, an inner experience, a first-person perspective. Physics can describe the brain's activity, can map every neuron, trace every signal. We can see which regions activate when you think about music or mathematics or memories of childhood, but nowhere in those neurons, nowhere in the electrochemical cascades, do we find the experience itself, the qualia, the redness of red, or the painfulness of pain. These seem to exist in a different category altogether from the physical processes that correlate with them. Some argue consciousness is an illusion, a trick the brain plays on itself, but it seems to miss the point entirely. Even if my sense of a unified self is constructed, even if what I think of as me is actually a collection of competing processes, there is still something experiencing that illusion. The experience itself is undeniable, is in fact the only thing I can be truly certain of. As Descartes said, I think, therefore I am. The very act of doubting proves that something is there doing the doubting. Could consciousness be fundamental rather than emergent? Some speculate that awareness might be a basic property of the universe, like charge or mass, present at some level in all matter, and only becoming complex enough to recognize itself in brains. This is called panpsychism. And while it sounds strange, perhaps it's no stranger than the alternative, that consciousness somehow springs into existence from purely unconscious processes. Or perhaps consciousness requires quantum effects, as Roger Penrose has proposed. Maybe the collapse of quantum wave functions, the transition from superposition to definite state, requires or involves something like observation, awareness. This would make consciousness fundamental to the quantum measurement process itself, woven into the fabric of physical law. I don't know. I truly don't know. It troubles me that physics, which has been so successful at explaining the objective world, seems to have nothing to say about the most immediate, most undeniable aspect of reality, subjective experience. Perhaps we need new concepts, new mathematical frameworks, that can encompass both the physical and the phenomenal, both the measurable and the felt. What I do find interesting is how consciousness, whatever it is, has allowed matter to understand matter, has allowed the universe to study itself. Through us, through human consciousness and inquiry, the cosmos has developed the ability to ask why it exists, to trace its own history, to predict its own future. We are not separate from the universe, not observers standing outside looking in. We are part of it, made of the same atoms, subject to the same laws, yet somehow able to comprehend those laws. And we wonder if we're alone in this capacity. Are there others out there, other conscious beings, other civilizations, other forms of life looking up at their own night skies and asking the same questions? The numbers suggest we shouldn't be alone. There are hundreds of billions of stars in our galaxy, hundreds of billions of galaxies in the observable universe. We've discovered thousands of planets around other stars, many in the habitable zone where liquid water could exist. The ingredients for life, carbon, hydrogen, oxygen, nitrogen, phosphorus, sulfur, these are common, created in stars and scattered through space when those stars die. Life arose on Earth relatively quickly in cosmic terms. Within a billion years of the planet's formation, possibly sooner, simple life had emerged. This suggests that given the right conditions, life might not be particularly unlikely. And if life is common, might intelligence also be common? Might consciousness? But we've found no evidence of other civilizations. We've listened with radio telescopes, searched for artificial signals, looked for signs of technology or engineering on cosmic scales. Nothing. The galaxy seems silent, empty of voices calling back to us. This is the Fermi paradox, named after Enrico Fermi, who asked, "Where is everybody?" Perhaps life is common, but intelligence is rare. Perhaps intelligence is common, but technological civilization is rare or short-lived. Perhaps civilizations arise but destroy themselves quickly through war or environmental catastrophe or some other filter we haven't yet encountered. Perhaps they're out there but so far away, so scattered across space and time that we'll never overlap, never communicate. Or perhaps we're truly alone, a singular instance of matter becoming aware in an otherwise unconscious universe. This seems both terrifying and precious. If we're alone, then consciousness, this strange, wonderful property, depends on us, on humanity, or whatever we evolve into, to continue, to spread, to persist. The universe would be counting on us, in a sense, to keep the light of awareness burning. But whether alone or not, whether consciousness is rare or common, fundamental or emergent, what strikes me is the responsibility it brings. We can destroy ourselves, can make the earth uninhabitable, can extinguish this light through negligence or malice, or we can nurture it, protect it, extend it, perhaps eventually carry it beyond this fragile planet to other worlds. The same intelligence that lets us split atoms and understand relativity also gives us the power to end ourselves. The same curiosity that drives science can be turned toward weapons, toward control, toward harm. Knowledge alone is not enough, you see. We need wisdom. We need ethics. We need to care about more than just understanding. We need to care about what we do with that understanding. I've often been asked about my role in the atomic bomb, about my letter to President Roosevelt warning that such a weapon might be possible, that Germany might be developing it. This letter helped start the Manhattan Project, and I've carried that weight, that knowledge that my equations E equals mc squared enabled this terrible weapon. I did not work on the bomb directly, was not involved in the project itself, but my physics made it possible, and my warning helped initiate it. And when I learned of Hiroshima and Nagasaki, when I saw what had been done, I wished I had never sent that letter. I said that if I had known the Germans would not succeed in developing the bomb, I would have done nothing. This is the dilemma of knowledge without wisdom, of power without ethics. Physics can tell us how to release nuclear energy, how to split atoms, how to build weapons of tremendous destructive power, but it cannot tell us whether we should, cannot provide moral guidance, cannot weigh human life and suffering against military necessity or political goals. And this extends beyond weapons. We're now developing artificial intelligence, editing genes, modifying our own biology, changing the climate of the entire planet through our industrial activity. Each of these capabilities comes from scientific understanding, from following curiosity about how things work. But the consequences, the choices about how to use these capabilities, these require something beyond physics, beyond technical knowledge. Perhaps this is why consciousness exists, why awareness evolved, not just to understand the world, but to care about it, to value things, to make choices that matter. A universe that only followed physical laws blindly would simply unfold according to those laws, meaningless, purposeless. But a universe that includes consciousness, that includes beings who can value and choose and create meaning, such a universe has something more, something that transcends mere mechanism. We are the universe's way of caring about itself, of valuing its own existence, of trying to ensure something worthwhile happens rather than just anything at all. There's something I want to tell you about time, about our experience of it, that goes beyond the physics, beyond the equations. We measure time with clocks, with atomic vibrations, with the decay of radioactive elements. We calculate dilations and curvatures, predict how clocks will differ between Earth and orbit, between here and there. But what is time really in our lived experience right now? This moment you're lying there, perhaps in darkness, perhaps with your eyes closed, listening to these words, and this moment it's unique. It will never come again. The particular configuration of thoughts in your mind, the specific sensations in your body, the exact pattern of sounds reaching your ears. This exists now and only now, never before, never again. Time is creating novelty constantly, each moment genuinely new, unrepeatable. We often think of time as a dimension like space, something we can move through or that we're embedded in. The equations encourage this view. Space-time is a four-dimensional structure where past and future exist as surely as left and right, up and down. From this perspective, your entire life, from birth to death, exists all at once, a four-dimensional shape in space-time. The sensation of moving through time, of the present moment advancing, might be just that, a sensation, not a fundamental feature of reality. But then why do we experience time so differently from space? We can move freely left or right, forward or backward in space, but in time we seem to move only forward, from past through present toward future. We remember the past, but not the future. We can change the future, but not the past. Time has an asymmetry, a direction that space lacks. Some of this, as we discussed, comes from entropy, from the second law of thermodynamics. Disorder increases toward the future, gives time an arrow. But is that the whole story? Does entropy explain why we experience ourselves as moving through time? Why there seems to be a now that advances, leaving the past behind and revealing the future moment by moment? I'm not sure it does. The feeling of time passing, of existing in a present moment that flows, this seems more fundamental than entropy, more basic than any physical process. It's tied up with consciousness itself, with the fact that we experience anything at all. Perhaps time's flow is not a feature of the universe, but a feature of awareness of how conscious beings process and integrate information. Or perhaps both are true simultaneously. Perhaps time flows in our experience precisely because we are conscious beings embedded in a universe with increasing entropy, with irreversible processes, with causation running from past to future. Our consciousness is itself a process in time dependent on memory, on the accumulation of experiences, on the transformation of present sensation into past memory and future expectation. What would it be like to experience time differently? Some people claim meditation can alter time perception, make moments expand or compress. During emergencies, time seems to slow down. People report experiencing events in slow motion, having time to think and react in what objective clocks measure as fractions of a second. This suggests our experience of time is constructed, malleable, not simply a passive reading of some external clock. And in dreams, time becomes even stranger, doesn't it? Events that seem to take hours occur in minutes. The sequence of events may be jumbled, non causal. You might dream of consequences before their causes, find yourself simultaneously in different times and places. Dreams hint at how contingent our normal experience of time might be, how dependent on the particular way our brains are organized and functioning. All of this makes me think that time is not one thing, but many things, depending on how you look at it. There's coordinate time in physics, measured by clocks relative to reference frames, dilating and curving. There's thermodynamic time, given direction by entropy increase. There's subjective time, the lived experience of duration and flow, and the present moment. And perhaps there are other aspects we haven't fully recognized or understood. The universe contains all of these times, all these perspectives, and we, as conscious beings, as physicists and philosophers, as experiencers and measurers, we participate in all of them. We are subjects experiencing time's flow and objects existing in space-time. We are both inside time, living moment to moment, and outside time, able to contemplate the whole structure, to write equations that treat past and future symmetrically. This dual nature, this ability to be both participant and observer, it's quite remarkable, really. We're not separate from what we study. Every measurement we make from within the universe, as parts of it. Every observation involves an interaction between observer and observed, both of which are physical systems obeying physical laws. And yet, somehow, despite this embeddedness, despite being made of the same atoms we're trying to understand, we can understand. We can discover laws that apply universally, including to ourselves. We can predict the behavior of systems far larger and far smaller than ourselves, can trace the universe's history from the Big Bang to the present and beyond, can grasp, at least mathematically, spaces and times and scales we can never directly experience. This is the gift and the mystery of consciousness, of mind, of whatever it is that allows matter to comprehend matter. We should never lose our sense of wonder at this, never take it for granted. The fact that you can lie there, relaxing, drifting towards sleep, and simultaneously contemplate the curvature of space-time, the beginning of the universe, the nature of time itself. This is extraordinary. And perhaps that's the real message I want to leave you with tonight. Not any particular fact about physics, not any specific equation or theory, but this: the universe is knowable, and you are part of it. And the act of understanding is itself part of the universe's story, part of what makes existence meaningful. Every question you ask, every moment of curiosity, every time you wonder why or how, you're participating in something profound, something that has been building for billions of years. The atoms in your brain were forged in stars, scattered through space, gathered into planets, organized into life, evolved into consciousness, and now they're thinking about their own origins. This is not separate from physics. This is what physics has been leading toward all along. Science is not finished, will never be finished. There will always be deeper questions, new mysteries revealed by each answer we find, and that's good. A universe completely understood would be a universe without wonder, without the joy of discovery, without that delicious feeling of standing at the edge of knowledge, peering into the unknown. So rest easy tonight, knowing that the universe still holds its secrets, still has room for mystery and wonder. The questions I couldn't answer, the puzzles that bothered me, they're still there for new minds to wrestle with, new perspectives to illuminate. And there will be questions we haven't even thought to ask yet, phenomena we haven't yet observed, connections we haven't yet seen. Before I let you drift off completely, I want to ask you if you found value in this journey through ideas. If these hours of contemplation have brought you something worth having, please take a moment tomorrow to like this video, to subscribe to the channel, to share it with others who might also find peace and wonder in learning. It helps more than you might think, helps us reach others who are lying awake, looking for something meaningful to think about as they fall asleep. And leave a comment, if you'd like, about what questions keep you awake, what aspects of the universe fill you with wonder. I'd love to know what mysteries call to you, what you find yourself thinking about in the quiet moments. But for now, let yourself rest. Let the thoughts settle like sediment in still water. The universe will still be here tomorrow, still mysterious, still beautiful, still waiting to be understood just a little bit better. The stars will keep burning, the galaxies will keep expanding, and consciousness will keep arising, keep wondering, keep reaching out toward understanding. Sleep well, dear friend. Dream of curved space-time and quantum superpositions, of distant galaxies and the beginning of time, or dream of nothing at all. Let your mind rest in the darkness from which all light emerges. Tomorrow, you'll wake to a universe that's simultaneously deeply understood and profoundly mysterious, and that's exactly as it should be. The cosmos is patient, its secrets will keep. And you are part of that cosmos made of stardust, animated by the same forces that light the sun and curve space around massive objects. You belong here, are woven into the fabric of existence as surely as gravity or electromagnetism. So good night. Good night to your wondering mind. Good night to your curious spirit. Good night to that part of you that reaches always toward understanding. May you rest in the knowledge that the universe is stranger and more beautiful than we ever imagined, and may you wake tomorrow ready to wonder anew. The universe whispers its secrets to those who listen, and sometimes the best listening happens in the silence, in the stillness, in that space between waking and sleeping where the mind is free to wander among the stars. Sleep now. The cosmos will wait for you. Good night.